Okay, this is approximately the fourth lecture in the live classes, and we're talking here about how to get the atoms in the barrier that are used in this tunneling measurement that we're talking about in this module. So they have a sample of atoms that are at extremely low temperatures that they use to be able to see the tunneling with a reasonable probability. And the starting point for this is getting to laser cooling, right? But laser cooling only gets you part of the way there, right? Gets you you need to get a factor of 100 or 1,000 colder than you can do with laser cooling before you get to the point where you can possibly start to look at this tunneling effect and measure the tunneling time. So the question is, how do you get this extra thing? How do you get this extra cooling factor that we need? And to answer that question, we need to also talk about the fact that there are very particular atoms that are used for these experiments. The Steinberg group is using rubidium atoms, and a question you could reasonably ask is, why rubidium specifically? Like, out of all the elements in the periodic table, why is that the one that you would pick? The answer has to do with the, sort of the messy details of atomic physics, which is that real atoms have not just two states that you can connect with a single laser frequency, but lots of different states. And this complicates your life, because if there are energy states in the atom that are higher in energy than the ground state of the atom, but lower in energy than the state that you're using to do as the upper state in your laser cooling transition, there's a probability that those atoms can decay into the wrong states. And once they're in the wrong states, then they don't interact with your laser anymore. You can't cool them down any further. So this, this is a problem you can fix by adding more lasers, but every time you add more lasers, it's harder to do the experiment in the lab, and these are plenty hard enough already. So this kind of limits the choice of atoms that you can use. If we look at the periodic table of the elements and ask, well, what atoms do people use to do laser cooling experiments? What we find is that these are mostly clustered on sort of the outer edges of the table. There's the noble gases have all been done, and the alkalis and the alkaline earths. The middle part of the table has a few atoms in there that have been laser cooled, but not so many. There's a lot of reasons for this, mostly coming down to the choice of the particular lasers that you need to use and how many additional lasers you need to make up for the fact that these atoms have all these extra states. Some interesting things about these different elements that have been cooled. There's a few of these that have really interesting properties. Chromium starts at a temperature of 1900 Kelvin, so almost 2000 degrees. That you need to heat it to before you can get enough chromium vapor to be able to cool it. And yet, starting at that high a temperature, they can still laser cool this very effectively. I mentioned that the rare gases, helium, all the way down through radon, those have all been laser cooled. Those don't start in the ground state. It turns out that the laser cooling transition that you use starts in a higher energy state that has an extremely long lifetime, and that opens a whole bunch of really interesting possibilities, which I say because that's what my PhD thesis research was in. There are also a number of these elements that have been cooled are radioactive isotopes. So francium and radium in particular, they have no stable isotopes. And yet people are able to do experiments where you can collect enough of these to trap them and study the properties of these extremely rare isotopes. So there's while the choice of elements that you can use is somewhat limited, it does span a huge range of properties, all the way from an atomic mass of about 3 up to an atomic mass of about 210, atomic number from helium at number 2, all the way up into the 80s. So lots of atoms, lots of possibilities. Given all that, why did they use rubidium specifically? So there's 3 aspects to rubidium that make it a particularly attractive element for laser cooling experiments. And I'll note it's nothing to do with the bulk properties of rubidium. Right? Rubidium is a sort of silvery metal, though that's a great thing to guess if anybody ever asks you to describe an element that you don't know anything about. Just say it's a grayish metal and you get like a 50% chance. The other thing with rubidium is it explodes violently on contact with water, so it's not fun stuff to have around under normal circumstances, but it's really good for laser cooling. Why is it good for laser cooling? One thing is that it has a very convenient laser wavelength. The laser cooling transition that people normally use is about 780 nanometers wavelength. That's in a range where the lasers that you use for that are the lasers that they use in CD players. So they're very, very cheap and plentiful, and it was for a long time very easy to get those lasers. And that makes these experiments very easy to do and relatively cheap. Another thing about that is they have a relatively convenient level structure. They don't have too many energy levels. And this is because it's an alkali metal. And so, consists of basically a bunch of completely full electron shells and then one outside electron. So it behaves almost like a single electron atom, which means that the level structure is a little simpler. There aren't so many bad transitions, and it makes it easier to do the things that you need to do to make laser cooling work. And that's a very nice feature if you're an experimentalist. But the most important reason why they do this is it's a boson. All right, so what does that mean? Well, this is one of many ways that physicists have of dividing the world into two categories of things. There are particles that we call bosons, and there are particles that we call fermions, and those two things have very different kinds of properties. All right. This leads to the phenomenon of Bose-Einstein condensation, which is critical for the carrying out of these experiments, right? They start with a Bose-Einstein condensate, which is a bunch of rubidium atoms that are almost at absolute zero. They're sort of as close to absolute zero as it's physically possible to reach. This is a phenomenon that's first predicted by Einstein is obviously Einstein, we all know him. And the other person involved is an Indian physicist named Satyendra Nath Bose, who predicted this in 1925. This has to do with these two classes of particles. Fermions are the ones that you're probably more familiar with, because if you took chemistry in high school, you spent a lot of time dealing with the properties of fermions. Right? Fermions are particles like electrons. They have a spin associated with them as if they were spinning balls of charge, though they are not literally spinning balls of charge. And that spin is described in half units. And this means that they have to obey what's called the Pauli exclusion principle, which says that no two fermions can exist in exactly the same state. And I say this, this is something that you've dealt with in high school chemistry, because if you do those exercises where you predict, right, how many bonds will a particular element be able to form, you spend some time drawing, an up arrow and a down arrow, and an up arrow and a down arrow, and you fill in these electron shells with up and down arrows, and that tells you how many bonds any particular element is able to form. Right, that is the Pauli exclusion principle. The up and down arrows represent possible orientations of this electron spin. One has its spin axis pointing up, the other has its spin axis pointing down. If you have two of those in the same energy level within an electron, that's it. You can't get another one in there. Right, so the next electron in has to go into a higher energy state. This is what fills up the orbitals and atoms. This is what leads to the structure of the periodic table. That leads to all of that stuff about which atoms are good for laser cooling and all that kind of thing. The other category of particles are called bosons, after Satyendra Nath Bose. And these are particles where fermions are sort of, if you want to be anthropomorphic, they're antisocial. You can never get two of them in exactly the same state. Bosons are the opposite. Bosons are gregarious. They like to be in the same state. And this is the thing that leads to the phenomenon of Bose-Einstein condensation, which is if you start with a gas of atoms at very high temperatures, they rattle around and collide with each other, bounce off each other, kind of like classical particles, like little billiard balls. As you cool that gas down, they start to show some of their quantum wave nature, right? They start to behave a little more like quantum wave packets. And if you keep cooling the sample and cooling the sample and cooling the sample, at some point the wavelengths of those particles get long enough that they start to overlap with each other. And when they start to overlap with each other, if those particles are bosons, then they realize, hey, we should all be in the same state together because that would be awesome. Right, and then they collapse into a single state, and that state's called the Bose-Einstein condensate. So it's sort of the ultimate in social distancing breakdown. These atoms realize that they all want to be together and group together into this Bose-Einstein condensate, and that is a sample of atoms that are all occupying a single quantum wave function, and that is as close to absolute zero as you can ever hope to get. So this is exactly the thing that we want in order to do these sorts of tunneling experiments. We want a lot of atoms that are all grouped together at as close to absolute zero as you can possibly manage. So how do you get Bose-Einstein condensate? Well, again, the part of the trick here is this is going to be done at very dilute gases, right? So it's not so dense that they all overlap with each other because they're all right on top of each other, in which case they would just form a solid, and a little lump of rubidium would fall to the bottom of your vacuum chamber. But there is a condition that we have that is, it says that the de Broglie wavelength of these particles needs to start to be comparable to the spacing between them. Or if we express that mathematically, we would say there's a de Broglie wavelength associated with atoms at a particular temperature that gets the symbol capital lambda, right? That's the wavelength of the atoms on average. And then we can talk about a density of the atoms. That's the number of atoms per volume. And if we want these things to be comparable to each other, and that we want the distance between atoms to be comparable to the spacing, or we want, we want that wavelength cubed defines a volume that if we multiply that by the density, we want that to be about 1. Right, we want there to be, 1-ish atoms per cubic de Broglie wavelength. At that point, then they're starting to overlap with each other, and you're going to get Bose-Einstein condensation. That means we want a low temperature so as to get the de Broglie wavelength to be as long as possible. That also means we want a relatively high density. The first place this is observed is in superfluid helium, which happens at a temperature of about 2 Kelvin, so that's a low temperature. And it happens at a density of about 10 to the 27 particles per cubic meter. That's a very high density, in large part because this is a phenomenon that takes place within liquid helium, right? The helium has glommed together to form a liquid, and that means that these particles are all, packed very closely together, interacting with each other very, very strongly. That's not what we want. Right. What we want is something that's going to be still a dilute gas. We want something that's going to start at a much lower density than that, which means we need to get the temperature much, much, much colder in order to reach the Bose-Einstein condensation threshold. How much colder do we need? Well, if we look at laser-cooled atoms as a starting point, right, the typical sort of numbers for this is, we can laser cool atoms down to a temperature of about a microkelvin. And we can have a density of kind of 10 to the 11 atoms per cubic centimeter. That's the units that atomic physicists usually talk about. You put that in SI units, that's about 10 to the 17 atoms per cubic meter. That's, millions of times less dense than air, right? So very, very dilute. If we ask what's the de Broglie wavelength there, it's a couple hundred nanometers, that sort of range. So, and then we ask what's the spacing, the density times that wavelength cubed, comes out to, 0.0006. Okay, so laser cooling is getting kind of into the region that we want, but we need to get much colder and much denser. And we can't do that with laser cooling by itself. We need another technique that will get us even colder than you can get by laser cooling, because laser cooling is ultimately limited by, what is that random kick you get every time the atoms emit a photon. So if they're scattering light, they're absorbing and emitting photons, they're never going to get much colder than the photon recoil temperature, and that's not cold enough. We need to get much colder than that. We need new techniques for doing that, and that set of techniques and how you make a Bose-Einstein condensate is going to be the thing that I talk about in the next video. So stick around for that, and we'll see you there.